Greetings, everybody. This example will hopefully indicate the vector nature of Newton's second law and how to break one or more forces into its x and y components, and then apply Newton's second law in both the x direction and in the y direction. Well, remember, Newton's second law is a vector equation. It's a vector sum. And it states that the sum of all the forces acting on an object equals the mass of the object times the acceleration. Well, remember, it's a vector. Vectors in general have, the real world is three-dimensional. Vectors have an x component, a y component, and a z component. But obviously, we're just going to deal with x and y. So in component form, you take the vector equation right here, and what it means is that the sum of the forces in the x direction equal the mass of the object times ax, in other words, the x component of the acceleration. The sum of the forces in the y direction equals may, and again, the real world is three-dimensional. The sum of the forces in the z direction equals maz. And then we write it in component form. The sum of the fx equals max, sum of the fy's equals may. Well, what that means is you have to draw each force acting on the object, or objects. We'll see where we have sometimes there are two or more objects involved in the system, but we'll get to that. But you draw all the forces acting on the object, and then, if need be, draw the x and y components of those forces. Now, you can have an object where if it's in what we call equilibrium, then in the language of physics, if an object is in equilibrium, then its acceleration is zero, meaning one of two things: either v is zero or v is constant. Because remember, which sometimes is called static equilibrium or just equilibrium. And you could also have a problem where an object is accelerating in the x direction but not accelerating in the y direction, or an object that is not accelerating in the x direction but it's accelerating in the y direction, or a case, as we'll see below, where it's accelerating in both the x and y directions, meaning, in this case, ax is not zero and ay is not zero. The first case would be an object accelerating along a horizontal surface, where, horizontal meaning in the x direction. So its ax is not zero, but if it's just moving on a horizontal surface, ay is zero. It's not moving up or down. Likewise, an example of the second would be an object in free fall, where its y acceleration is not zero. It's negative 9.8 meters per second squared. But an object in free fall is clearly not moving in the x direction. And as we'll see below, what if an object is accelerating in both the x and y directions simultaneously? Well, again, the approach is always the same. The rubric is the same. Draw all the forces acting on each object in the problem. That's then why in the previous lectures we have to know how to draw those four forces. If you can't draw them, you're done. How can you determine their components? Then, if need be, unless they're entirely in the x or entirely in the y direction, if they're at some angle relative to the horizontal. Remember, we deal with the reference angle, the angle relative to the x-axis. Resolve them into their components. Important. Just basic right triangle trig. Then apply Newton's second law to each object, and remember also, sum of the forces in the x equals max, sum of the forces in the y equals may. Then, once you finish step 3, you're going to yield a set of one or more equations. Now, algebra is your friend. You're going to solve these equations for the unknown variables. And don't worry, we're going to do several examples, so don't let that frighten you. Well, let's look at an example right here. It's a hockey puck, and it has a mass of 0.3 kilograms. And it's sliding on a frictionless horizontal surface of an ice rink. So the ice rink represents the horizontal ice rink is the horizontal XY plane. And again, no friction, so we're good there. Now, two hockey sticks strike the puck simultaneously, and they exert forces F1 and F2 as shown in the figure. It's as if we're hovering directly above the ice rink and we're looking straight down at this puck. F1 has a magnitude of 5 newtons. It acts at an angle of 20 degrees below the x-axis. F2 has a magnitude of 8 newtons. It acts at the puck at an angle of 60 degrees above the x-axis. Don't overthink it. F1 is in Q4, F2 is in Q1. F1 acts at an angle of 20 degrees as shown. F2 acts at an angle of 60 degrees as shown. Magnitude of F1, i.e. simply the hypotenuse of what's going to be a right triangle. Magnitude of F1 is 5 newtons. Magnitude of F2 is 8 newtons. Well, components, clearly F1 and F2, clearly each of them, they're each going to have an X component and a Y component. How do you get them? Basic right triangle trigonometry. Don't overthink it. Well, down here in my solution, I'm going to go ahead and do the components. Well, let's look at F1. I'm going to call the 20 degree angle, looking at F1, I'm going to call that angle theta. For F2, I'm going to call the 60 degree angle, I'm calling that angle phi. That's the Greek letter phi. And here, that's the Greek letter theta. So F1, in other words, what we're saying is F1 makes an angle of theta with respect to the x-axis. We know, given from the given information, F1 is in Q4. F2 makes an angle of phi with the x-axis. We know from the given information, F2 is in Q1. Okay, well, let me just start with F1. So the angle 20 is my theta. So notice F1 is going to have an x component. F1 has an x component and a y component. I'm simply drawing a right triangle with F1 as the hypotenuse. Well, notice here's F1. Well, the y component, remember, it's always going to be sine. Remember, that's why we deal with what's called the reference angle. So the y component of F1 is going to be F1 sine theta. Now here's where you just want to be careful. Because F1 is in Q4, I know that the y component, I know that F1 sine theta is going to be negative. That's why right there, it's going to be negative. Okay? Now what about the x component of F1? Well, that's going to be, now see the dotted line, that F1 cosine theta, see, I'm saying that the dotted line, that F1 cosine theta, that's this red vector right here. And that's going to be F1 cosine theta. But again, don't overthink it. Remember, when you're using the reference angle, no matter what it is, y is always, in general, y is a sine theta, x is a cosine theta. In this case, the vector a, the hypotenuse, is F1. So the y component is F1 sine theta. The x component, this red vector right here, the longer one, that's F1 cosine theta. Just note to self, F1 sine theta is negative. Okay, now let's resolve F2 into its components. Well, here the angle is phi, which we know is 60. The y component of F2, the y component of F2 is F2 sine phi. And we know because F2 is in Q1, that y component is positive. Well, what's the x component of F2? It's F2 cosine phi. This red vector right here. They're both positive. Why? Well, just look at the figure. F2 is in Q1, so it's x and y. Any vector who's in Q1, its x and y components are going to be positive. But it's basic, don't overthink it, it's basic right angle trig. Because we always deal with the reference angle, we know right away. Y component of F1, F1 sine theta. X component of F1, F1 cosine theta. Just note to self, F1 sine theta is going to be negative. Why? Just look at the, why is it negative? Look at the figure. F2, Y component, F2 sine phi. X component, F2 cosine phi. They're both positive. Okay. So now here, let's get the x and y components of F1 and F2. So So f1x is f1 cosine phi, right there, this red vector right here. f1y is minus f1 sine theta. Why? Not the letter y. Why is it negative? Because f1 is in Q4. Its y component is going to be negative. There we go. I've taken care of it right there. Now what about f2? The x component is f2 cosine phi. The y component is f2 sine phi. And don't let the subscripts confuse you. You know, they can seem a little bit cumbersome. But f1x, that's just saying, what is the x component of f1? f1y, that's the y component of f1. f2x, x component of f2. f2y, y component of f2. Now I have to go ahead and apply Newton's second law to that hockey puck. But I have to apply it in both the x and y directions. I have to do it separately. You cannot add apples and oranges. You cannot add x's and y's together. You have to have two separate equations. One where you apply Newton's second law in the x direction, sum of the fx, and one where you apply Newton's second law in the y direction, sum of the fy's. Okay, let me do the x direction first. So the sum of the fx's is equal to max. What this means is take all the forces in the x direction and simply add them up, whether or not they're positive or negative. You can have negative terms in the sum, but it just means add them all up. Well, notice both forces in the x direction are positive. Just look at your diagram, or look up here. So the sum of the forces in the x direction, of which there are two, there's f1 cosine theta and f2 cosine theta. Add them up. Well, what does that sum equal? Well, it equals the mass of the hockey puck times the x component of the acceleration. Now, why am I solving for ax? Well, what does the problem ask me for? The problem says determine the magnitude and direction of the puck's acceleration. Meaning magnitude, Pythagorean theorem. Meaning to use the Pythagorean theorem, I need the x and y components. Direction, meaning I want the quadrant and the angle. So note to self, whenever I ask for magnitude and direction, by the magnitude, I mean I want the magnitude you get using the Pythagorean theorem. To use the Pythagorean theorem, you need to get the x and y components. By direction, I want to know what quadrant is the final vector in, and I want to know what is the angle. So again, let me go back. Sum of the forces in the x direction equals max. Well, what two forces are acting in the x direction? f1 cosine theta and f2 cosine theta. They're both positive. What does that sum equal? M times ax. Solve for ax. Nothing complicated. Ax is given by this equation. We know f1 and f2. We know theta. We know phi. We know m. Plug in numbers. You get ax is 29 meters per second squared. And notice it's positive. Okay, now let's do the same thing. Let's apply Newton's second law in the y direction. The sum of the fy's equals may. Well, what forces are acting in the y direction? Well, look at your figure. You have f1 sine theta and f2 sine phi. But remember, f2 sine phi is positive, f1 sine theta is negative. So when you add them up, it's going to be f2 sine phi minus f1 sine theta. Because again, the f1 sine theta is negative, meaning you got to subtract it. So you have f2 sine phi minus f1 sine theta equals may. Well, solve for ay. Just some trivial algebra. So I wanted to change that. So you take this equation, solve for AY. You're just dividing both sides by M, likewise in the previous step. So again, you know F1 and F2, you know phi, you know theta, you know M. So plug in the values, you get 17 meters per second squared. Now notice, AX and AY, the X and Y components of the net acceleration vector, AX and AY are both positive. Then you know the net acceleration is in Q1. Okay? Now let me go ahead and get the Pythagorean theorem to get A. A is equal to root AX squared plus AY squared. You get 34 meters per second squared. Then I'm going to use the arctan, the inverse tan, arctan means the same thing. I'm going to use that to get the angle. I'll call that angle alpha. Alpha is equal to the arctan of AY over AX. Plug in AY, which is 17, AX is 29. You get 30 degrees. I know it's in Q1. So this is a final complete answer. A is equal to 34 meters per second at 30 degrees in Q1. And that's it. That's how you apply Newton's second law in this case in the X direction and in the Y direction. Let me go ahead and save this video and get it posted.